Hello everyone, welcome back to my channel. Today we are going to discuss a new paper called Multitask Learning for End-to-End ASR Word and Utterance Confidence with Deletion Prediction. This paper I think it was submitted to archive a couple of weeks back. I think this is a submission for Interspeech 2021 and the authors are, these are the authors, and the paper is coming from Google. So in the tutorial we are going to cover first the overview of the paper, then we'll see the proposed approach, finally we'll see some experiments and results. So as the paper name itself suggests, so this paper is about estimating confidence of ASR predictions. It could be word level confidence or utterance level confidence. So what do I mean by confidence estimation? So imagine you have a speech recognition model, especially assume you have a end-to-end speech recognition model using, for example, transformer or LSTM, and the architecture will have an encoder and it will have a decoder, right? So what happens is you will take the audio and feed it through the encoder. Encoder applies multiple transformations using different layers. If it is transformer, it uses multi-head self-attention. If it is LSTM, it uses LSTM units, and the output of which will go to the decoder, and the decoder will try to predict the sequence of words, or it could be sequence of characters. Let's say I say hello here and I get sequence of characters HHALELLO, or if it is a subword you will get word pieces, and this is how the end-to-end model works. And for many downstream speech applications you will need confidence of these words. So why do we need that is, for example, let's say you want 100% accurate transcription for your application, but obviously no speech recognition model as of today can give you 100% accuracy or 0% WR. You will know, I mean you know that your model can make a mistake, and you want to find out where it has made a mistake or where it is not so confident, at which part of the output the model is not confident, right? So what you could do is you can find out the confidences of these words, or let's say your output is I am going to school, and you want to know how confident is the model when it was predicting the word I, and how confident when it was predicting am, and so on, right? And that is word level confidence. Or you also sometimes you want to know, okay, what is the confidence of this entire sentence? If it is, let's say, 99%, then you know that the accuracy of this sentence, or accuracy of this sentence is really good, right? Something like that. Now going back to the old classical confidence estimations or old classical speech recognition models like hybrid models, what they used to do is they have a search graph where they know the boundaries of these words, and they could just take the posterior probabilities of all the frames and compute the confidence. That was very easy. Like for example, if you are using CALD, you can use a alignment command. It is going to find out the word level timestamps, and then it computes the or it sums up all the log probabilities of the frames within that timestamps, and that will be your confidence. So if the model is very accurate, you will have a very good or a high posterior probability, so that will give you high confidence, right? So in the classical systems it is really good, but in case of end-to-end we don't really get this kind of word level timestamps. You might have to add another forced alignment module separately. It is a bit complicated, but the question is, how do you integrate everything into a single framework so that you get confidence of words and utterances, and also you'll get the transcript, right? So that is the question question we are asking here. So the idea of this paper is to build some new approach, or propose a new approach to predict the confidences of the ASR outputs both at word level and at sentence level, and we will see how they do that. And they use something called a multitask learning approach to achieve this task, and we are going to understand that in the coming slides. like I said, multitask learning with multiple objective functions to get confidence of the outputs, or the confidence of the hypothesis from the ASR modules. And you can also so that is one thing. So getting the confidence of the sentences or the predictions, it's an important thing. And also they show that using rescoring mechanism, you can also improve the word accuracies or the WR of the system also. So we'll see how that is done in the coming slides. Now we'll understand the proposed approach in details in this section, and I have divided into 5 different sections. And it's just a warning that the paper is a bit mathematical. I'm going to explain it as much as I can, but just a warning that it has a lot of equations and so on. First we will see the model, what is the architecture, and the overview of the picture or overview of the paper. And we will see some baseline word level confidence estimation, like how people have or how this word level confidence estimation is done, or also known as CEM module integration is done in the previous papers. And we will see the new proposed idea in this paper is called deletion and prediction. It's a different task which they have which you can assign to the speech recognition module, so that it improves the performance. And also we'll see the utterance level confidence estimation block, and these are the 3 tasks which we are going to use for the multitask learning training, and that I will explain in this 5th section. The architecture looks like this. What happens here is you have these acoustic frames, which are MFCC frames, or any spectral features, and so on. And then you have an encoder, and typically encoder will be an LSTM or a transformer. In this case they are using the transducer. So you have this RNNT encoder, assume it's a LSTM, right? They have stacks of LSTM layer, and the output of the LSTM layer will be called as A. So imagine A is a acoustic or higher level acoustic features, right? So after high level acoustic feature, after the encoder, and then you have a decoder, and the decoder is this decoder, as you can see, this is the decoder. So it takes the word pieces. So imagine word pieces as I think many people will be knowing about what word piece is. Let's say if I give you a sentence transcript, for example, let's say good morning, right? And good morning is 2 words. You can use sentence piece or sentence piece library, which is available for free, and use that to cut this sentence into subwords. So the subword chunking basically uses a different mechanism altogether, but assume you have the sentence piece library, you feed this transcript and gives you subwords, right? So the subwords will be something like this, go, od, more, something like that, right? So these are the pieces, word pieces. Sometimes they are also called word pieces. So this is good because modeling entire word is very hard, because you may have thousands and thousands of words. So let's say 200,000 words, and you may not get good amount of or enough examples to model a particular word. So modeling every word is an extreme thing. People don't usually try that, even though there are there are research papers which people have tried, but that requires large amount of, huge amount of data. Modeling character level is a good thing. People have tried previously. It's a very good thing. If you have small data, it's easy to model, because they are there will be only limited number of characters in a language, 40, 50 and so on. But that is a lower extreme. The question is how are we going to use the the question is how can we model something in between, like a subword, right? Subword is basically, it's not a word or it's not a character, so it's something like in the middle. You may have 6,000 or 10,000 subwords in a language. Not exactly in a language, you can mention how many ever you want, but depending on the data set, you can say, let's say I want 10,000 subwords for this data set, and those subwords you can use them directly to map every sentence into those subwords space. and then these subwords, like I mentioned here, these subwords can be used as input to the decoder, and the decoder takes two inputs. One is this A, which is the acoustic features or higher level acoustic representations from the encoder, and that will be used for the cross attention module. Cross attention is nothing but similar to self attention, but instead of providing same key value and same query and value, you provide key from acoustic encoder but value and query from acoustic encoder but provide key and value from the decoder. So that's why it's called cross attention. And you have self attention, which basically uses the embeddings, the subword embeddings as a query key and value, right? And you can say my output f of this one, f of y1, y2, so on, ym is nothing but function mapping. Let's call it as let's say this is a transformer, not transformer. Let's say it's a some function which has cross attention and it has self attention. So let's call B as this embeddings. This B1, by1, by2, and so on. They are all embeddings, subword embeddings, and A is acoustic features. And combining these two, I mean the decoder takes these two and provides this function of y1, y2, and so on, right? So f of y2, so on, right? So these are outputs from the decoder. So if you have, let's say in this case we have 4 subwords, and you get 4 different vectors at the decoder, right? Now we'll come to the real deal, which is the real idea of this paper, which is there are 3 different modules here, and this module is this provides something called word level loss. We'll understand what that is in the coming slide. Then the second module provides something called deletion loss, and the last one provides something called utterance loss, utterance level loss, right? LUTT, L deletion, and L word, right? Now for the word level loss module, what I want to model is, this is the standard module people use for any confidence level confidence estimation ideas for end-to-end models. What they do is they take the outputs, the word level outputs. So f of w1 basically means the feature vector for the word w1. So just remember, we don't want so just remember y is called subword, right? And w1 or w is called word, right? So there is a difference between word and subword. Word is basically, for example, this morning, this entire thing is a word, and this mor and ing, both are different, they are subwords, right? So y is called subword and w is called word. So this module takes the words. I will tell you how these words are taken in the coming slide when I am explaining this whole module. But just assume you get this words and you provide it to softmax layer, and the softmax layer will predict 3 outputs, and it says whether it's a correct output, whether it's insertion, whether it's a substitution, right? So what are insertion and substitution? In a simple way, if you are computing WR, you must be knowing what is insertion, substitution, and deletion is, because you want to calculate the WR. So what is insertion is, insertion is basically, instead of predicting one word, you have predicted another word, you inserted, right? Sorry, not in you instead of predicting nothing, you have predicted something, right? So that is insertion. Substitution is you have replaced the words, like original output is replaced by some other output. Deletion is you have deleted the output, right? So similar something like that. Now we want to just predict only these things. We are not predicting deletion here. We will see we will be modeling deletion separately. We'll see that later. In case of this module, you are just predicting whether the word is correct, or it is inserted, or it is substituted, right? So these are 3 neurons, or these are three labels which you are predicting at this softmax layer. So just assume the softmax layer has 3 neurons, and just correct probability of insertion, probability of deletion, right? And they are denoted like this. And how do you compute word level loss? We'll understand that in the coming slide. Similarly, you have deletion loss. I will explain deletion loss in the coming slide. Similarly, you have utterance loss. Utterance loss is to get the utterance level confidence. We will see how that is done in detail with some mathematical equations and so on. And this is the final score. You use all these scores, and you use all these three losses, which you just sum all these losses with some scores. Weighted sum of all these scores will be the final loss, and use that to back propagate through the neural network. So assume that our assumption is that you are fixing this network fixed. I mean, this network is fixed, it's frozen, because this is a speech recognition module. You just want to update this network. We will see the layers, number of layers and all, whatever is present in this module. And that is how the training is done. So I hope you guys understood the block or the architecture of this paper. We are going to understand these blocks in detail. Don't worry about that. So let's see. Let's go and understand each block separately. So the first block is provides you the word level loss. I think I forgot to mention that. So this word level loss looks like this, but before that, let's get some notations. So like I said, f of y1 is the feature representations from the decoder for every subword, right? You have m subword. M is the number of subword, and L is the number of words, right? L is number of words. And L will be less than or equal to M sometimes, but usually M will be higher because there are more subwords, and number of words in that sentence will be lesser, right? So the transformer is just a function mapping, takes the encoder output A, applies cross attention, takes the decoder input B, and applies self attention, and this function mapping will give you the sequence of vectors. These are the subword vectors or subword features from the decoder, right? Now we are going to take every one of these vector, send it through MLP, multi-layer perceptron, 2-layer, 3-layer, how many ever layers you want. Then you have a softmax which predicts 3 classes, or predicts an output with 3 dimension, and the class labels for each is correct, insertion, substitution, right, for every subword, right? But we don't want to calculate the loss using the subword, but we want to calculate the loss for every word, right? Now how are we going to do that? We have subwords, but we want to compute loss for every word. So obviously we can map the subwords into words easily, and the loss is computed like this. So you just want to sum all the losses together. So assume you have 3 losses, or 3 you have 3 predictions. You just want to compute the log sum of all these predictions. So hypothesis is like this. For example, just giving an example of how do you map the subwords into words, or subword loss into word level loss. See, hypothesis has this is the hypothesis is the prediction from the model. So it has only predicted go morning. So the ground truth is good morning. So like you see here, you have 4 subwords, but there are only 2 words, as you can see here. Good is one word, morning is another word, and the hypothesis has predicted 3 subwords. But one of them is wrong, obviously. Good is wrong because it is predicted good as go, and morning is correct. Now as you know, we have so there is no prediction for good, so it has just substituted the word good by go. So you have added the loss s of sw, which is the substitution of the word 1, and the second word, for second word you have predicted it correctly, and you are just adding the correct loss, which is cw of w2, and as you know, there is no deletion, so it's just not adding anything. So the total loss is for the word total loss is the sum of these 2 losses, right? As simple as that. And if you have third word, it will just go on. All right, so as simple as that. Now that is what is represented in this equation, and to compute the mu's WCR, so the WCR is word correct rate, just like we have word error rate, and just sum of all the correct words divided by total number of words, right? As simple as that. So I hope you guys understood what this word level confidence estimation. This is the baseline approach. And the idea of this paper is to add multiple of these kind of objectives to improve the performance, right? So this deletion length prediction is another task which is proposed in this paper. So what it does is we will understand what the idea of this deletion length prediction module. So the idea is, assume you have a random variable ej, and j could go from 1 to L plus 1. So L here is basically, as I said, the number of words in the predictions, in the hypothesis, right? Now EJ can take three different things. So first thing is, if j equal to 1, you will have the EJ variable will have to predict the number of deletions before the first word. If j is L plus 1, it takes the number of words prediction after the last word. And if j is if j is between j if in between, if it is not 1 and L plus 1, it has to predict the number of deletions between the word j minus 1 and jth word, right? Now like I said, this is the random variable, and you can compute the expectation of the random variable. So the assumption here is, they assume this random variable is Poisson distributed. The main reason is, Poisson distribution is used for modeling counts or rates. For example, if you want to find out the number of customers entered a hotel at a given particular time, you can use Poisson distribution. Similarly, for many other count related or rate calculation related things, people use Poisson distribution. Similarly, even here, to compute the number of deletions for a given word, they can just use this Poisson distribution, and the expectation of the Poisson distribution is computed like this. Here R of W, RW of Wj is basically transformation through an MLP of this word feature given the parameters theta, right? And the final loss, the loss is basically looks like this, is a cross entropy, the maximum likelihood loss. Ej is the correct instance or correct number of deletions for the given word Wj. Given this and the predictions, you can just compute the maximum likelihood of this L of this sequence of words W1, W2, and so on, and then the loss will be L deletion, and this loss is going to be added to the previous loss L word along with some weightage, and there is going to be one more loss. I will explain what that loss is, and you can compute the WR using this equation, and this equation, some of these numbers are calculated like this. Then coming to the third loss, which is word level confidence estimation. So the idea of this is, instead of predicting the confidence for every word, you can directly predict the confidence of the entire sentence, right? So entire utterance. So how do you do that? So to compute the loss, we can't directly predict it. We have to create some way or some architecture which will predict the confidence. But you have to train it first, right? Before predicting, you have to train it during the training so that it predicts or it generates during testing. Now assume you have a utterance, and what we are going to propose is, we have to say it is 1. The score is 1 if the word error is 0, otherwise it is 0, right? This is hard decision, but these we can't realize in the neural network because these are discrete. You have to create a soft version of this. For that, you can simply use some sort of softmax. So softmax related thing, something like softmax, because it is soft version of this thing, so that you can differentiate during the training. So assume you have this the feature, subword feature. It goes through some transformation, W1. Assume it is some neural network or some linear layer with some activation tan h and the bias, right? So this UI, we can use it to compute the attention weights, right? This is the exact attention equation. Like if you remember, this is the first attention paper, 2014 Yoshibenju's paper. This is attention equation. So once you get the attention weights, you can simply scale the features with the attention weights and then sum all of them and then pass it through an NMLP and a sigma. You will get the you will get the prediction mu utterance, and that will be between 0 and 1, and you can use the cross entropy loss or binary cross entropy loss to compute the loss for that utterance, and you will get the third loss. So now the thing is, you just have you have three losses. So L word is the first loss, and you have L so this utterance is another loss, and you have the previous one which you computed. I think it's called deletion or something, right? So these three losses we have, and you can just add all the three losses and then create this final loss, which is this loss, which is sum of scaled weighted sum of three different losses, and then you can use this loss to back propagate through all the three modules, and then train the module, right? So as simple as that. So I hope you guys understood. I think it was a little bit lengthier, but let's just go to the experiments and see what is the accuracy. So in the experiments, this is as I said, this is the Google paper. So they are using their own internal data sets to train and evaluate all the models. But the architecture looks like this. It has 8 LSTM layers in the encoder and 2 in the decoder, or in the prediction network. Sorry, this is RNNT transformer. So RNNT architecture, which is the transducer, it has the encoder and the prediction network, and you have the LSTM layers are unidirectional with 2048 units, and projection layers to reduce the times between the layers, like in the third and second layers. And as I said, the RNN transformer or the transducer network, the speech recognition transducer network is frozen during the CEM training. So CEM stands for confidence estimation module. Now, as I said, you have three different modules. L deletion is the second module. It has three layers of MLP with output dimension of 320, 160, and 1, because you just want to predict 1 here, right, in the output. Similarly, the L utterance also has it has two MLP layers and hidden dimension 320, and you want to predict 1 because you are predicting the confidence estimation for the entire sentence. So it's either 1 or 0, or it can be in between also. It can be, if it is 0.5 or if it is 0.9, you can say the utterance confidence is 0.9, right? So the output is 1 for L utterance and L deletion. And this is something which you can note down for, not really note down, just know that this is something, these are different models for which they have computed the accuracy. Coming to the training data, as I said, they are using the internal data sets, Google's internal data sets, which contain search, far field, like in Google Home, and telephony and YouTube data, and these are coming from different domains. So you have to do multi-style training with some downsampling and all those. So, and for the testing, they are using 14,000 voice search audio calls, voice search audios. Like when you ask some questions in Google or in OK Google, so those are the utterances they are using for testing. And for LM, they are using some 10,000 sentences from maps data. So that is about the data set. Coming to the result section, so they have multiple tables for the results. So I am just showing only one table. The remaining tables you can read the paper and understand. I have given the link of the paper in the description. The results, as you can see, as I said, there are different models. There are 5 different models, and when you combine the utterance loss and the deletion loss along with word loss, you don't get that level accuracy for the word level prediction, because you are combining the utterance loss, which may not be useful. But for utterance level predictions or utterance level confidence, you get the best AUC and WR, right? And for word level, it's enough to have only word level loss and the utterance level loss. So the deletion loss is actually helping you for improving the utterance level confidence, utterance level confidence accuracies, and for word level confidence, only the deletion loss is not so much useful. And same thing, this is for the voice search test, and this is for the long tail maps. And that's all for this tutorial. Thanks very much for watching this tutorial. If you have any feedback, please write them in the comment section. I'll try to answer them. Thank you.